What if I told you that the deadliest weapons platform ever deployed on a battlefield required no batteries, no satellite links, and no microchips, yet could operate continuously for weeks in conditions that would disable a modern combat drone in minutes? We are accustomed to thinking that precision-guided missiles and autonomous robots represent the pinnacle of military engineering. But Roman siege machines prove otherwise. These mechanical marvels could hurl 60-kilogram stones over 400 meters with repeatable accuracy, operate in torrential rain and desert heat, and be completely rebuilt from local materials in less than 3 days. Watch the video to the end to find out how Roman engineers achieved battlefield dominance through mathematical elegance rather than electronic complexity, and why their maintenance philosophy would revolutionize modern military logistics. Roman siege warfare was not just crude catapults and battering rams, but a sophisticated integration of ballistics, materials science, and mass production that wouldn't be matched until the Industrial Revolution. Their artillery systems did not depend on rare earth metals mined from a single geographic location, were not vulnerable to electromagnetic pulse attacks, and functioned flawlessly in the mud of Germania, the sands of Judea, and the frozen steppes of Dacia, where today's lithium-ion batteries would fail catastrophically. It was a triumph of modular design, field repairability, and physics-based engineering that transformed siege warfare into a predictable science 2 millennia before the first computer simulation. The Ballistae, Onager, and Scorpio represented 3 distinct weapon classes, each optimized for specific tactical roles, yet sharing a common mathematical framework. The torsion spring technology that powered them, the standardized construction methods that made them universally deployable, and the training systems that created expert crews formed an integrated weapons ecosystem. This comprehensive approach to artillery warfare anticipated modern combined arms doctrine by nearly 2,000 years. Understanding Roman siege machines means understanding that true military superiority comes not from technological complexity, but from reliability, adaptability, and the systematic application of fundamental principles. What if I told you that Roman military engineers possessed a universal formula that allowed them to build artillery of any size, anywhere in their empire without blueprints, CAD software, or even written instructions? Roman siege machines were not based on trial-and-error tinkering by individual craftsmen, but on a rigorous mathematical system that made their artillery completely standardized across 3 continents. The main secret was not the shape of the projectile or the type of wood used, but a single critical measurement: the diameter of the hole through which the torsion springs were threaded. This fundamental dimension, calculated from the weight of the ammunition or length of the bolt, dictated every other proportion of the machine through a series of fixed ratios. An engineer who knew he needed to throw a 25-kilogram stone could instantly calculate the spring hole diameter using the formula: diameter equals 1.1 times the cube root of 100 times the projectile weight in Greek mine. From this single number flowed the length of the frame arms, the thickness of the main beams, the dimensions of the trigger mechanism, and even the number of sinew strands in each torsion bundle. A ballista designed to shoot a 2-foot bolt in Britain would have identical proportions to one shooting the same length bolt in Syria, differing only in absolute scale. This meant that the Romans did not need to transport complete siege engines across their empire, an impossibly cumbersome task given the weight and bulk involved. Instead, they transported only the metal components: trigger mechanisms, washers, frame pins, and bronze spring housings. These precision-made parts, manufactured in imperial arsenals to exacting standards, could be fitted to wooden frames constructed on-site from local timber. A legion marching into Gaul carried the brain of their artillery, while the body could be harvested from any suitable forest along their route. The system's elegance lay in its self-correcting nature. If an engineer attempted to use a frame beam that was too thin for the spring tension, the mathematical ratios would immediately reveal the error. The beam length would not match the required multiple of the spring hole diameter. This built-in quality control prevented catastrophic failures in combat. The machines were engineered with substantial safety margins based on empirical testing under maximum loads, ensuring that components failed gradually and obviously rather than explosively and without warning. This standardization enabled a level of logistics sophistication that would not be seen again until the Napoleonic era. A damaged ballista in one part of the empire could receive replacement parts manufactured hundreds of miles away, with complete confidence that they would fit perfectly. Legion artillery crews could be rotated between different machines without retraining. Because all Scorpios had identical controls, all Onagers had the same cocking mechanism, and all Ballistae used the same sighting principles. It was interchangeable parts manufacturing, the foundation of modern industry, implemented in wood, iron, and twisted sinew. Compare this to modern military robotics, where a damaged servo motor from a specific manufacturer's production run may require weeks of procurement through Byzantine supply chains. A faulty circuit board in a contemporary drone often means the entire unit must be shipped back to the original manufacturer. The Romans built their war machines to be maintained by the soldiers who operated them, using tools and materials available in any military camp. They understood that complexity is the enemy of reliability, and that a weapon system's true measure is not its maximum performance under ideal conditions, but its minimum performance under the worst possible circumstances. The Golden Module system represented a philosophical approach to engineering that valued universal compatibility over specialized optimization. Modern militaries customize and upgrade their platforms continuously, creating a nightmare of version incompatibility and training challenges. Roman engineers resisted the temptation to improve the proven ratios, recognizing that standardization itself was a force multiplier worth more than marginal performance gains. This discipline maintained artillery interoperability across 4 centuries of Roman military dominance. Be sure to subscribe to our channel right now so you don't miss the next analysis of ancient technologies that solved problems we still struggle with today. We are very interested in hearing your point of view. What do you think about implementing such radical standardization in modern military equipment? Would the loss of cutting-edge performance be worth the gains in reliability and maintainability? Write about it in the comments. Want to know a secret that will change your understanding of energy density? Roman siege machines didn't burn chemical propellants or compress gases. They twisted organic fibers to store mechanical energy with an efficiency that modern composite springs struggle to match. At the heart of every ballista and Scorpio was a torsion spring bundle, a carefully prepared assembly of animal sinew that could be wound to extreme tension. Hold that energy indefinitely and release it in a fraction of a second with devastating effect. The material of choice was not ordinary rope or even treated leather, but specifically processed tendons from the neck and legs of cattle. These collagen-rich fibers possessed a unique combination of properties: exceptional tensile strength, remarkable elasticity that allowed extreme deformation without permanent damage, and resistance to fatigue, failure, even after thousands of tension cycles. The preparation process was labor-intensive and required specialized knowledge. Fresh tendons were thoroughly cleaned of all meat and fat, then dried under controlled conditions to prevent brittleness. Next, they were soaked in a vinegar solution that chemically modified the collagen structure, increasing its resilience. Finally, individual fibers were combed straight, twisted into cords, and treated with oil to maintain flexibility and resist moisture absorption. A single torsion spring bundle for a medium ballista contained over 200 meters of prepared sinew, twisted into a dense rope as thick as a human arm. These bundles were threaded through bronze or iron-reinforced frames and then pre-tensioned using a sophisticated windlass system. The critical innovation was this pre-tensioning. The springs were wound far beyond what would be required for a single shot, creating enormous stored energy even in the relaxed state. When the throwing arms were drawn back to firing position, they added only marginal additional twist to springs already near their maximum capacity. There is a fascinating historical account documented by Josephus during the siege of Jerusalem in 70 CE. When the Roman 10th Legion exhausted their supply of prepared sinew during the prolonged siege, the engineers ordered the systematic collection of hair from the legion's pack animals and ultimately from the women in their camp followers. Human hair, though inferior to cattle tendon, possesses sufficient tensile strength and elasticity to function as emergency spring material. The women cut their braids, knowing that each contribution might provide a dozen additional shots against the city's defenders. This dramatic sacrifice demonstrated not just the technical versatility of the torsion system, but the desperation of siege warfare and the human cost embedded in every mechanical component. The real genius lay in the tuning process. Engineers tensioned the twin springs of a ballista or Scorpio by sound, literally listening for the proper pitch. A properly tensioned bundle, when struck, produced a clear musical tone at a specific frequency. If the left and right springs sounded different notes, the asymmetry would cause the projectile to veer off target. Master artillery craftsmen developed perfect pitch for these mechanical tones, able to detect tension imbalances that would cause a miss at 300 meters. They would tap the spring bundles with a small hammer, comparing the resonant frequencies, then make micro-adjustments to the tension screws until both sides rang in perfect harmony. Compare this to modern artillery, which relies on precisely manufactured metal springs or hydraulic systems. Metal springs suffer from fatigue and permanent deformation. They weaken with use and must be replaced on strict schedules, regardless of actual condition. Hydraulic systems require sophisticated seals that fail when exposed to sand, extreme cold, or simple age-related deterioration. The Roman torsion spring, properly maintained, could last for years and gave clear warning of impending failure. Sinew fibers fray and show visible wear long before catastrophic breakage. An observant crew could spot a developing problem and retension or replace individual cords before the spring failed during combat. This technology proved that biological materials, carefully selected and processed, could outperform manufactured alternatives in demanding applications. Modern composite bow technology, used in Olympic archery and hunting, has only recently achieved energy storage densities comparable to Roman torsion springs, and at vastly greater cost using carbon fiber and aerospace-grade resins. What I am about to show you would be classified as an anti-personnel directed energy weapon if it existed today, specifically designed to target enemy leadership and create psychological paralysis through precision elimination. The Scorpio was not an area weapon, but a surgical strike platform, the ancient world's first true sniper system. It was a torsion-powered, bolt-shooting machine capable of engaging individual human targets at ranges exceeding 300 meters with first-shot hit probability that modern infantrymen with scoped rifles would respect. The Scorpio differed fundamentally from its larger cousins through its emphasis on rapid engagement cycles and precise aiming mechanisms. A two-man crew could achieve a sustained rate of fire approaching one shot every 15 seconds. One operator controlled traverse and elevation while continuously tracking the target, while the second loaded the bolt and drew the bowstring using a simple cocking lever. This division of labor created a weapons team capable of engaging multiple targets in quick succession, similar to a modern designated marksman team. The ammunition was not a simple, oversized arrow, but a carefully engineered projectile. Scorpio bolts were crafted from seasoned hardwood for the shaft, fitted with pyramidal iron heads designed to concentrate impact force on a minimal surface area, and stabilized with wooden vanes cut to specific aerodynamic profiles. The bolts were balanced so precisely that the center of gravity fell exactly 1/3 of the distance from the tip. This proportion maximized penetration while maintaining stable flight. A well-made Scorpio bolt could punch through a bronze breastplate at 200 meters or penetrate a wooden shield and the man behind it at 100 meters. Historical chronicles confirm that during Julius Caesar's campaigns in Gaul, Scorpio crews routinely targeted Gallic chieftains, identifiable by their distinctive armor and elevated positions. The psychological impact was devastating. Barbarian leaders learned that visibility meant death. They saw warriors standing beside them suddenly collapse with massive trauma wounds, killed by projectiles they never saw coming. The flat trajectory of the Scorpio meant there was no warning whistle of an incoming arrow arcing from above. The target simply ceased to exist in an instant of catastrophic impact. This created a command paralysis in enemy formations. Leaders who took cover couldn't effectively control their troops, but leaders who remained visible to coordinate attacks were systematically eliminated. Interestingly, Roman engineers developed graduated sighting mechanisms for the Scorpio that functioned as primitive range-finding systems. The frame of the machine bore etched marks corresponding to different elevation angles, were calibrated for engagement ranges in 50-meter increments. Experienced crews learned to estimate distance by visual cues, the apparent size of the target, the clarity of facial features, the relationship to terrain landmarks, and translate those estimates into sight settings. This system allowed for effective indirect fire against targets behind partial cover, with spotters directing adjustments based on observed impacts. Unlike modern sniper rifles that require extensive training to achieve consistent accuracy, the Scorpio's mechanical nature meant that much of the precision was built into the device itself. A competent operator could achieve lethal accuracy within days of training, because the machine controlled the critical variables of release timing and aim stability. Modern military snipers spend months mastering trigger control, breathing discipline, and reading environmental conditions. A Scorpio crew needed only to master the simpler skills of target estimation and mechanical adjustment. This machine proved that mechanical precision could deliver tactical effects previously requiring extraordinary individual skill. The Romans democratized long-range precision fire, making it available to ordinary legionaries rather than reserving it for a small elite of expert archers. Don't forget to like this video if you were impressed by how the Romans developed precision engagement capabilities 2,000 years before laser rangefinders and ballistic calculators. Don't forget to subscribe to the channel so you don't miss any new videos. Are you ready for the shocking truth about how Romans reduced stone fortifications without explosives? So the Onager was fundamentally a kinetic energy weapon, converting the slow mechanical work of human muscle into the violent, instantaneous release of stored torsion energy. Named for the wild donkey because of its vicious kick when fired, this single-armed torsion catapult could hurl stone projectiles weighing up to 80 kilograms across distances exceeding 400 meters. The Onager operated on a different mechanical principle than the two-armed Ballistae. A single massive throwing arm was inserted through a horizontal torsion bundle at the machine's base. Drawing this arm backward twisted the bundle to extreme tension, storing enormous energy. When released, the arm rotated violently upward until it struck a padded crossbeam, the sudden stop transferring all its momentum to the projectile cradled in a leather sling at the arm's tip. This whipping action dramatically multiplied the arm's velocity, launching stones at speeds approaching 100 meters per second. The projectiles were not random rocks, but carefully shaped ammunition prepared by specialized stone-cutting teams. Spherical stones were preferred because they maintained consistent trajectories and achieved maximum range for a given mass. These projectiles were roughed out using iron hammers and picks, then refined by patient grinding against abrasive stones until they achieved near-perfect roundness. Quality control was enforced through calibration rings, bronze hoops of precise diameter. A stone that wouldn't pass through the ring was too large and would produce unpredictable flight characteristics. A stone that passed through too easily was undersized and would waste the machine's energy potential. There is a remarkable account from the Siege of Masada in 73 CE, where Roman engineers adapted their onagers to throw not just stones, but ceramic vessels filled with incendiary compounds. These primitive firebombs shattered on impact, spreading burning oil mixed with pitch and sulfur across wooden defensive structures. The innovation demonstrated the versatility of the platform. The same machine that could breach walls could also deliver chemical weapons, biological agents, diseased animal carcasses were documented, or even propaganda, containers of threatening messages or severed heads. Modern artillery maintains this tradition of projectile versatility, but requires extensive engineering to develop compatible munitions for different effects. The sound of an onager firing was psychologically devastating. The creaking tension of the windlass as the arm was drawn back, audible hundreds of meters away, signaled an incoming bombardment. The sharp crack of the arm hitting the crossbeam carried like thunder across the battlefield. Then came the peculiar whistling howl of the stone in flight. Some engineers deliberately drilled holes in projectiles to enhance this effect, creating screaming stones that terrorized defenders. Finally, the catastrophic crash of impact, pulverizing masonry and flesh with equal efficiency. This acoustic signature created panic even among troops not directly threatened, as the sound promised indiscriminate violence beyond any individual's ability to evade. Interestingly, Onager crews became highly skilled at calculating indirect fire missions. Using simple geometry and surveying instruments, they could engage targets completely hidden behind walls or hills. Spotters positioned on high ground would observe the impact and signal corrections using flags or mirrors. Through iterative adjustment, crews achieved remarkable accuracy against unseen targets. One historical account describes a Roman battery systematically destroying grain storage buildings deep inside a besieged city, targeting structures they could not directly observe based solely on intelligence reports of their location. This anticipated modern artillery forward observer techniques by 2 millennia. Compare this to modern towed artillery, which requires extensive crew training, complex fire control computers, and continuous ammunition resupply through vulnerable logistics chains. The 155mm howitzer system costs millions of dollars and breaks down frequently under field conditions. The Onager could be constructed on-site for the cost of skilled labor and basic materials, operated by crews trained in weeks rather than months, and maintained using tools available in any blacksmith shop. When ammunition ran low, any suitable stones could be shaped into projectiles using simple hand tools. This reveals a fundamental truth about weapons design. Reliability and field sustainability often matter more than maximum performance. The Onager was not the longest range or most accurate siege weapon theoretically possible, but it was the most practical weapon that could be deployed anywhere and maintained under any conditions. Which modern weapon system do you think best embodies this philosophy of robust simplicity over fragile complexity? Write your thoughts in the comments. In the next chapter, you will learn how Roman artillery crews achieved consistent accuracy without electronic rangefinders, ballistic computers, or even Arabic numerals. using only empirical observation, geometric principles, and accumulated expertise passed from master to apprentice. Roman gunnery was not guesswork, but a systematic discipline based on understanding projectile physics. The key position was the librator, literally the leveler, the artillery specialist responsible for aiming and fire control. This individual underwent years of training to internalize the relationship between spring tension, elevation angle, projectile weight, and range. They developed an intuitive understanding of ballistic trajectories that modern artillerists achieve through computer modeling and extensive range time. The aiming process began with a registration shot using a standard projectile of known weight. Observers positioned at elevated vantage points would watch the impact and communicate the deviation from the target using flag signals or voice commands. Based on this feedback, the librator would adjust the machine's elevation and traverse. Elevation was controlled by a threaded screw mechanism that raised or lowered the rear of the machine's frame, changing the throwing arm's release angle. Traverse adjustments were made by physically shifting the entire machine using levers and rollers, or for smaller Scorpios, by a rotating base platform. What made this system work was standardization. Because all machines of a given type used identical spring tensions and projectile weights, the librator could rely on memorized range tables. These were not written documents, but knowledge embedded in the practitioner's mind through endless repetition. A librator knew that for a standard ballista shooting a 2-foot bolt, a specific elevation mark on the frame produced a range of 250 meters. Doubling that elevation angle added approximately 75 meters. These relationships were approximately logarithmic, and experienced operators developed an intuitive feel for the curve. For engaging targets at unknown distances, Liberatori used geometric surveying techniques. A simple instrument called a dioptra, essentially a sighting tube mounted on a calibrated base, allowed measurement of angles relative to the horizon. By measuring the angle to the top of a distant wall and knowing the observer's height above ground, the librator could calculate the wall's height using similar triangles. Knowing the wall's height and measuring the angle from a different position gave the distance through geometric calculation. This system required no advanced mathematics beyond basic proportion, well within the capabilities of soldiers trained in elementary arithmetic. There is a documented instance during the Siege of Jerusalem where Roman artillery engineers used night firing techniques to maintain psychological pressure on defenders. During daylight, they carefully aimed their machines at specific targets: gate mechanisms, guard towers, visible command posts. They then locked the machines in position using wooden wedges and marked their orientation on the ground using stakes and string lines. After dark, crews could fire blindly, confident that their projectiles were still aimed at the daytime targets. This created the terrifying impression that Roman artillery never slept, maintaining accurate fire around the clock. Defenders attempting to repair damage under cover of darkness would suddenly be killed by precisely aimed shots arriving from invisible machines. The system's genius lay in its progressive refinement. Each shot provided data that improved subsequent accuracy. A modern fire control computer processes this feedback loop in milliseconds. Roman crews processed it in minutes, but the fundamental principle was identical. They understood that even with imperfect information, systematic observation and correction would eventually produce hits. This patience and methodology allowed them to engage targets that seemed impossibly difficult, destroying specific sections of wall, collapsing particular towers, eliminating identified command posts. Compare this to modern artillery, which has indeed gained the ability to achieve first-round hits through sophisticated sensors and computer modeling. However, this capability evaporates when GPS signals are jammed, when computer systems are damaged by shock or moisture, or when crews are forced to operate in degraded modes. Roman fire control, being entirely mechanical and human-dependent, had no degraded mode. It operated at full capability under any conditions where humans could survive. This robustness came from embedding expertise in trained personnel rather than fragile electronics. Surprisingly, their methods of calculation without zero or decimal notation yielded results sufficient to conquer the known world. Romans used whole numbers and fractions, performing calculations that seem impossibly cumbersome to modern minds accustomed to calculators. Yet these methods produced artillery fire accurate enough to decide the fates of nations. This demonstrates that mathematical sophistication is not required for practical success, only the systematic application of sound principles. What if I told you that I discovered this principle while analyzing after-action reports from contemporary conflicts in Afghanistan, where sophisticated weapon systems became useless because of broken parts that couldn't be replaced in theater? The fundamental challenge of military technology has never changed. Weapons must be maintainable under field conditions by the soldiers who use them, or they become liabilities rather than assets. Roman siege engines embodied a radical approach to this problem. They were designed from the ground up for complete field reconstruction. When a ballista's throwing arm cracked under stress, legionaries didn't requisition a replacement from Rome. They walked into the nearest forest, identified a suitable ash or oak tree, felled it, and shaped a new arm using basic carpentry tools. The standardized proportions meant they knew exactly what dimensions were required. There was no guessing, no trial and error, just the application of the golden module ratios to produce a component guaranteed to fit. Metal components represented the only irreplaceable elements, and these were specifically designed for longevity. Trigger mechanisms, washers, frame pins, and spring housings were forged from iron or cast in bronze, materials that don't degrade unless subjected to extreme abuse. These parts could outlast multiple wooden frames, being simply transferred from a damaged machine to a newly built one. A trigger mechanism forged in Rome might serve in Britannia, be salvaged from a destroyed machine in Germania, refurbished in a Gallic workshop, and end its service life in Syria, a 50-year career spanning the empire. The wood used for machine construction was not random lumber, but carefully selected timber with specific mechanical properties. Oak provided strength and density for load-bearing frames. Ash offered flexibility and shock resistance for throwing arms. Elm resisted splitting for components subjected to lateral stresses. Roman engineers were practical dendrochronologists, understanding that trees grown in different climates and soils possessed different characteristics. An ash tree from a windy hillside, forced to develop dense wood to resist constant bending, was superior to valley-grown ash for making throwing arms. This botanical knowledge was as critical as their engineering expertise. Interestingly, the Roman army maintained dedicated workshop centuries, specialized units of craftsmen who traveled with the legions to provide field maintenance and construction capabilities. These military engineers carried portable forges for metalworking, carpentry tools for woodworking, and most importantly, the standardized metal components needed to build siege machines. When a legion laid siege to a city, these workshops would establish themselves nearby and begin mass-producing artillery. Contemporary accounts describe workshops producing a complete ballista every 2 days during active siege operations, a rate of manufacture that would be impressive even with modern power tools. This modular philosophy extended to the machine's construction. A ballista wasn't a single integrated device, but an assembly of interchangeable subcomponents. The torsion spring assemblies could be pre-built as complete units, tested and stored. Trigger mechanisms were standardized modules that fitted any machine of a given class. Even the frames were often constructed in sections that could be assembled on-site and disassembled for transport. This approach anticipated modern military container systems, where standardized modules can be combined in different configurations for different missions. Compare this to contemporary military robotics, where a damaged circuit board often requires factory-level diagnostics and repair. Modern combat drones are marvels of miniaturization and integration, which makes them nearly impossible to repair in the field. A Roman legionary with basic carpentry skills could restore a damaged ballista to service in hours. A modern infantryman with a broken drone must typically send the entire unit back through the supply chain, waiting days or weeks for a replacement. The cost of this fragility is measured not just in dollars, but in lost capabilities during critical operations. The durability of Roman machines was enhanced by their tolerance for damage. A ballista with a cracked frame could still fire, though at reduced range. A Scorpio with worn torsion springs could still engage close targets. A damaged Onager could be adjusted to throw lighter projectiles. This graceful degradation stood in stark contrast to modern binary systems that either work perfectly or fail completely. Roman engineers understood that warfare is chaotic and designed their equipment to remain useful even when damaged. Do you think modern military equipment should prioritize field repairability over maximum performance? Or is the capability gap created by cutting-edge technology worth the logistical vulnerability? The Romans made their choice. They selected sustainable adequacy over fragile superiority and built an empire that lasted 1,000 years. Roman siege machines became a thing of the past, not because they were obsolete, but because the civilization that created them collapsed. With the fall of the Western Roman Empire in 476 CE, the mathematical knowledge of the Golden Module, the craft secrets of sinew preparation, and the standardized training systems of the Liberatory were lost. Medieval Europe reverted to simpler counterweight trebuchets, crude gravity-powered devices that were easier to build but far less capable, because the institutional knowledge of torsion mechanics had vanished. We admire these machines today because they represent the perfect synthesis of sophisticated design and practical execution. This is a lesson for modern engineering across all domains. The best solution is not always the one that pushes the boundaries of materials, science, and computational power, but the one that can be deployed, maintained, and operated in the real world under adverse conditions. Roman siege artillery was the AK-47 of its era, not the most advanced theoretical design, but the most effective practical weapon system. Studying their construction methods, we see that many components of modern cranes, winches, and mechanical systems have direct lineage to Roman military engineering. They invented ratchet mechanisms to prevent backsliding under tension loads, developed bronze bearings to reduce friction in rotating assemblies, and created laminated spring systems by layering materials with different elastic properties. These innovations appeared in Roman siege machines centuries before their discovery by European engineers during the Industrial Revolution. We stand on the shoulders of giants who wore sandals and lorica segmentata rather than lab coats. Roman siege machines proved that human ingenuity can transcend material limitations. Without high-grade steel, petroleum-based lubricants, or precision manufacturing equipment, they created weapon systems that conquered the Mediterranean world. This demonstrates a profound truth. Technology is merely a tool, and true capability emerges from systematic thinking, disciplined execution, and institutional knowledge preservation. A society that maintains these qualities will dominate regardless of its material resources. We have seen that Roman siege machines were not primitive precursors to modern artillery, but the pinnacle of pre-industrial military engineering, combining mathematical rigor, material science, and tactical flexibility in ways that modern weapons often fail to match. They surpassed their contemporary counterparts in reliability, maintainability, deployability, and operational sustainability. They were ideal force multipliers, mechanical soldiers that required no food, felt no fear, obeyed without question, and could be rebuilt indefinitely from local materials. The history of Roman siege artillery is a master class in robust design written in timber, iron, and twisted sinew. Which aspect of Roman siege machine design did you find most impressive in terms of engineering philosophy? Was it the mathematical standardization that enabled universal interoperability, or the field maintenance approach that prioritized sustainability over peak performance? Write your opinion in the comments, and don't forget to subscribe to the channel to continue exploring the ancient technologies that solved problems we still struggle with today.